Now let's talk about continuity. We're going to say that a function is continuous over an interval if you can complete the sketch without picking up your pencil. Now we're going to have a much better definition later when you take calculus. But this is good enough for now. So let's look at each of these functions and see where the function is continuous. I see if I start on this function right here, and I start at negative infinity, and I come in, I'm going to have to pick my pencil up here at 0 where there's a hole. All right? So we're going to say that this function is continuous from negative infinity to 0, and from 0 to positive infinity. And it's discontinuous at x equals 0. For this function, now it's not necessarily a pretty function. It zigzags around, but as I trace it, I don't have to lift up my pencil. So it's continuous from negative infinity to positive infinity. There are some functions you simply must know. The identity function is a line. F of x is equal to x. The domain is all reals. The range is all reals. It's increasing over the entire domain, and it's continuous over its entire domain. You can graph points, x, y, and of course it's a line. In this case, the identity function goes through the origin. You have to know the squaring function. Y is equal to x squared. Domain is negative infinity to positive infinity. The range is from 0 to infinity. It is decreasing from negative infinity to 0, and it's increasing from 0 to infinity. And it's a continuous on its entire domain. You must know the cubing function. The domain is all reals. The range is all reals. This function is increasing on its entire domain, and it's continuous on its entire domain as well. You must know the square root function. The square root function has a domain from 0 to infinity, and it does include 0, and a range from 0 to infinity. It is increasing on the interval 0 to infinity, and it is continuous on the entire domain, 0 to infinity. You have to know the cubed root function. The cubed root function has a domain negative infinity to positive infinity, and a range of negative infinity to positive infinity. It is also increasing over its entire domain, and it is continuous over its entire domain. The absolute value function, f of x is the absolute value of x, is defined to be a piecewise function. It's defined to be x when x is greater than or equal to 0, and negative x when x is less than 0. The graph of the absolute value function, it's this kind of V-shaped pointed. The domain is all reals, and the range is from 0 to infinity. Now, the absolute value function is decreasing from negative infinity to 0 and increasing from 0 to infinity. It is continuous over its entire range. Now, a piecewise function is just a function where it is defined by different rules over different intervals. And so we're always going to write a piecewise function, usually with the brackets, and then we'll have some f of x for x is greater than or equal to some number, often 0, and some g of x when x is less than 0. So that's what we mean by a piecewise function. We write it in pieces. So let's graph this piecewise function. You see, this function is defined to be 2x plus 4 when x is less than 1, and 4 minus x when x is greater than or equal to 1. So you want to graph each over their domain separately. So when x is less than 1, f of x is 2x plus 4, and it has an endpoint of 1, 6. But that is not included in the graph because we have that strict less than there. To find another point, you You can pick any point you want since it's a line. So you can pick 0. So y is 4. When x is 0 of 2x plus 4. So you draw a ray starting at 1, 6 and goes through 0, 4. So that's the first piece of your piecewise function. Now when x is greater than or equal to 1, um, it's going to be defined by 4 minus x. For the second part, when x is greater than or equal to 1, then f of x is 4 minus x. So you want to check the endpoint, put in x equal 1. We see 1, 3 is included in the graph because we have that equal sign. Now we want to pick another point. You can pick any point you want, but let's substitute in x equal 4. When x is 4, y is 0. And so we'll have a ray that starts at 1, 3, goes through 4, 0, and extends. So this graph right here, this is a piecewise function. You can see as it's divided into pieces. And again, you graph the first line and only include parts of it when x is less than 1. And then you graph the second line, being careful with your endpoints. And it is only defined when x is greater than 1. So suppose I want to graph f of x is negative x minus 2 when x is less than or equal to 0, and f of x is x squared minus 2 when x is greater than 0. Graph each separately. When x is less than or equal to 0, you check the endpoints. Put in x equals 0. So 0, negative 2 is included as part of the graph. Now you just pick another point. And if we pick negative 2, we get y is 0. So you have a ray starting at 0, negative 2, and going through negative 2, 0. So this is the first piece of your graph. Now for the second part, when x is greater than 0, if you check the endpoint and you put in 0, 0, negative 2 is not part of the graph because we have that strict inequality there. There's no equals. You can pick another point, say 2, 2, and you can have another ray. Again, this is going to be a quadratic though. So when you do the first part, here is your line. In this case, 0, negative 2 is included on the graph. These two happen to coincide at the endpoints. This often does not happen. Often you're going to have a jump. But in this case, it is included. And it's a quadratic, so you pick up several points to graph, and you get yourself a nice quadratic curve there. The greatest integer function is a really cool function. It means f of x is the greatest integer, and you can tell greatest integer because we're always going to do it with this double bracket. It'll be like this. Kind of hard to see on my diagram here. All right, and it is the greatest integer that is less than or equal to x. So while the domain is all reals, the range is the integers. And it is discontinuous at every integer value. It has this jump here. So at 0, it is 0. At 1/2, it is still 0. At 3/4, it's 0. At 1, it is 1. At 1.5, it's still 1. At 2, it jumps up to 2. At 2.5, it's 2. So it's just a really kind of slick function.